Hi students, welcome back to Vijay Datta chemistry classes. This is Purnima ma'am. Today we are going to start with states of matter. In the states of matter, we are going to discuss gas laws and ideal gas equation. Right? Uh, Let us start with the introduction. Here, states of matter generally we'll discuss the three types of states generally. Those are first one is the solid state, second one is the liquid state, and third one is the gaseous state. So this solid state we'll study in the 12th standard, and this liquid state, due to this pandemic this year they were deleted this portion from the this year, yes, in the first year. The next gaseous state, this gaseous state we are going to start now. Okay, see, now in the gaseous state, first of all, the very important we have to start what are the properties of the gases, right? So, what are the properties of the gases? And our first one we are going to see in this video the properties of gases. Next, gas laws. What are those gas laws? First one is the Boyle's law. Second one is the Charles law. Third one is the Avogadro's law. Boyle's law, Charles law, and Avogadro's law also we are going to discuss here. Charles law temperature 1, 2 we can discuss Avogadro's law, and also Gay-Lussac's law, and next ideal gas equation. Next one, ideal gas equation. These laws and this ideal gas equation I am going to explain in this video. Okay students, let us start. First of all, first of all, come to the gas properties. See, different properties we have. Solids has the properties, liquid has the properties. Like that, only gases also have some gaseous properties. What are the characteristics of the gaseous state? That is nothing but if you are considering one substance that has a some properties, means it will have some characteristic properties. What are those general characteristics of the gases? Okay, those we can study as the physical properties. So what are the physical properties of the gases? First of all, the first property is the gases are highly compressible. These gases are highly compressible, these are compressible. That's why while the cooking gas, that is we are compressing into the cylinder, isn't it? That one we are using for the cooking purpose. And also gas, if you see the scent bottles and all, in that also we are seeing the gas only that is compressing into that bottle. So gases are highly compressible. That is the first physical property. And the second one, they exert pressure equally in all directions. Gases can exert pressure, gases will have a pressure, that pressure will be equal in all directions. The gases exerts pressure equally in all directions. Equally in all directions. And the next one, next physical property is these gases have the lower density. Density of the gases is less than the solids and liquids. When compared with the solids and liquids, the density of the gases are lower when compared with the solids and liquids. And one more, volume and shape of the gases are not fixed. It will see, even the liquids also that will take the shape of the container, whereas come to the gases they will not have any volume, and they'll not have the particular shape. Gases that this shape like that, they don't have any particular shape and particular volume. No particular shape and volume for the gases, shape and volume for the gases. And also here they mix evenly. They will mix evenly. Gases will mix evenly and completely. If you want to mix two gases, they'll mix evenly and completely without any mechanical aid. Okay, without any mechanical force or anything to apply, they can mix easily. Suppose you are taking hydrogen and nitrogen, they can mix easily because they have a gap between their molecules. Suppose see here, this is the container. In this the gas molecules will be arranged like this. More space, more space like this they will be arranged. That's why whenever the gas is leaking, the smell will spread throughout the room immediately. Like that only, if you are spraying the scent bottle, the smell of the scent bottle spread evenly throughout the room, isn't it? So the molecules, the forces of attraction between the molecules is negligible, and the distance between the molecules is more. So distance between the molecules present in the gases are more, and the forces of attraction between the molecules are very less. That's why they can spread immediately, evenly and completely throughout the room without any mechanical aid, right? These are the general properties of the gases, ma. Okay, see, this one we'll study in the lower standards only. Let us start with the gas laws. Let us start with the gas laws. See, the first one we are going to discuss is the Boyle's law. The first law is the Boyle's law. What is the Boyle's law? This one, this Boyle's law we can known as pressure volume relationship. Pressure volume relationship. So this Boyle's law also known as pressure volume relationship. Okay, see here, how to statement, what is the statement of the Boyle's law? This statement of Boyle's law we can say, at constant temperature, statement, at constant temperature the pressure of a at constant temperature, because it is a pressure volume relationship, right? So we are keeping the temperature constant. At constant temperature the pressure of a fixed amount, the pressure of a fixed amount is nothing but the number of moles are fixed. The fixed amount of a gas, the fixed amount of a gas is inversely proportional to its volume, inversely proportional to its volume. This is known as Boyle's law. Okay, see here, at constant temperature means you are taking the temperature constant, then we want to bring the relationship between the pressure and volume. How will be that pressure and volume? Pressure is inversely proportional to the volume. Then I want to remove this proportionality constant. Then P equal to K by V, where K is called constant. So we can write PV is equals to K, means constant. If you are taking this PV equal to K constant, if you are taking the same law for two different gases, then we can take it is as P1 V1 is equals to P2 V2. For two different gases you are taking, P1 is the volume of pressure of the first gas, V1 is the volume of the first gas, P2 is the volume of the second gas, and V2 is the volume of the second gas. Then according to the Boyle's law, this is Boyle's law statement, this Boyle's law statement was given by Robert Boyle in 1662. He was proposed this law. Generally, when the pressure, volume, temperature, at these three parameters at constant temperature, pressure is inversely proportional to the volume. The pressure of a fixed amount of a gas is inversely proportional to its volume. Means volume is less, then pressure is more. Because if you take one container, this volume till here volume is there, you have taken one piston, and you are pushing that piston inside, means you are applying some pressure. You are applying some pressure. How much pressure you are applying, means how much pressure you applied on the piston, that much this volume will be decreases, amount of the gas will be decreases. So pressure, more amount of pressure you are you are applying, then volume will be decreases. This is the law he has been proposed. So this is P proportional to 1 by V, P equal to K by V, PV equal to K at two different gases, P1 V1 equal to P2 V2. This only we can write as P1 by P2 is equals to V2 by V1. This is also Boyle's law, like we can say. See, by taking this relationship, we can draw the graphs. We can draw the graph. See, at constant temperature, if you are drawing a graph, those are said to be isotherms. At constant temperature, the graph drawn is called isotherm. Constant temperature, the graph drawn is called isotherm. So for the Boyle's law, whatever the graph we are drawing, that graph is said to be isotherm. Here we can take two types of the graphs, that is pressure is on one axis and volume is on this axis. Then see here, pressure we have taken on x axis and sorry, volume we have taken on x axis, pressure on y-axis. Then actually pressure and volume both are inversely proportional to each other. Then pressure, volume is increasing, then pressure should decrease. Then volume is increasing, then pressure should decreases. So the graph we p proportional to v, if you are taking this graph, then we are getting this is called hyperbola. We are getting the graph like this, because both are pressure is decreasing when volume is increasing. Okay, this graph is said to be isotherm, because at constant temperature we are drawing this gas. So if you are taking the different values, if you are taking different values, we are getting the different graphs. That is nothing but at different temperatures. Say 200 Kelvin, we can here 400 Kelvin and 600 Kelvin at different temperatures. If you are taking, then we are getting the different curves we can observe at the given mass of a gas. And also the graph will be vary by varying the temperature. If you are taking 200 Kelvin, you are taking the curve like this. By 400 Kelvin, you are getting the curve like this. By 600 Kelvin, we are getting the curve like this. So at constant temperature, we are drawing this graph is called isotherm, and higher curves corresponds to higher temperature. Then the curve increases by increasing the temperature like. And also it should be noted that volume of the gas doubles if pressure is halved. Volume of the gas is doubling, then pressure becomes the half. That is nothing but volume is increasing, then pressure should be decreases. Okay, see, this is the first graph, the graph between the P and V. Suppose if you are taking the graph between the plot the graph between P and 1 by V. So on one axis I am taking the pressure P, and another axis I am taking the 1 by V. See, pressure is inversely proportional to V, but pressure is directly proportional to 1 by V. Here P 1 by V, we are taking directly 1 by V. So the relationship between the pressure and 1 by volume is directly proportional. Directly proportional is nothing but pressure is increasing, then volume also increases at different temperatures. At different temperatures, suppose it is the T1, it is the T2, and it is the T3. You are taking the T3 different temperatures, then this T3 is greater than T2 is greater than T1. Then this is also the graph against to the 1 by V between the pressure. Okay, so in this condition, it is a straight line passing through the origin. When we are taking P proportional to 1 by V, the graph we are getting is straight line passing through the origin. Okay, high pressure, see, you are applying the more amount of the pressure, that the gases deviates from the Boyle's law. Such conditions straight line will not be observed. You are increasing tremendously the pressure, then will not observe the straight line, then the deviates the Boyle's law. Okay, so this is about the Boyle's law. Okay, see, And also here one more thing we can know that highly compressible. Whatever the gases we are taking, that gases are highly compressible when a given mass of gas is compressed. So, whatever the gases are highly compressible in nature, then P proportional to 1 by V. Then we'll get the straight line passing through the origin correct only because gases are not compressible. Then volume cannot decrease. Due to that reason, pressure is inversely proportional to uh, V. That is the Boyle's law. That depends upon the nature of the gases. Generally, gases are highly compressible, but some gases again they'll have their individual properties. Some of the gases are highly compressible and some of the gases are little bit less compressible. Again the factor will vary which type of gases we are considering also. Okay, so this is about the Boyle's law. Next come to the Charles law. So before going to the Charles law, here we can bring the relation between the density also. So, what is the exact the Boyle's quantitative experiment it is giving? It is proving that gases are highly compressible. When the gases are highly compressible, because of that, mass of a gas is compressed. When a given mass of gas is compressed, see here, it is the container. In this gas is there. By applying the pressure through the piston, the mass of this gas is compressing. Compressing is nothing but suppose in this 10 molecules are present, but you are applying the pressure, the 10 molecules are not decreasing, the 10 new molecules are not becoming 9 molecules or 8 molecules. The place occupying by the 10 molecules in the container is decreasing. That is nothing but density is increasing. So when you are applying the pressure, then the density of the gas is increasing. Then we can say pressure is directly proportional to the density. You got my point. See here, if you are taking the volume till here by through the piston, you are applying some pressure, right? So you are applying the pressure. As the gases are highly compressible in nature, then the gas starts compressing and the gas came to here. Then actually till here also it has 10 molecules. By compressing to here also it has the 10 molecules. That is nothing but the space between the molecules are decreasing. The space between the molecules decreasing is nothing but density of the gas is increasing. So if you are applying the pressure, then the density of the gases are increasing. Then P proportional to D. How can we bring this relation? Already we know that density is equal to mass by volume, right? But already according to the Boyle's law, what is the relation we know? Volume is equals to K by P. Volume is equals to K by P. Simply if you substitute that one here, M by K by P. So by cross multiplication, I can write this D is equal to M by K into P. Suppose this M by K into P, M by K as taking mass and mass as the constant, like if you are considering D is directly proportional to P. So as the gases are highly compressible, then density is directly proportional to the pressure. Okay, this is also explained according to the Boyle's law, brought the relation between the density and the pressure. Okay, so this is the special case in the Boyle's law. Now come to the next one, Charles law. Next law is the Charles law. See here, this Charles law is also known as temperature volume relationship. This is called temperature and volume relationship. In this temperature and volume relationship, this is first given by Charles and Gay-Lussac. These two scientists has proposed so many several experiments they have been performed on the gases independently to improve the hot air balloon technology. That is, again, we'll study in the payload like some topic. So, a hot balloon, they have done some experiments based on this. So, after the so many investigations, what is the conclusion they have given? At the fixed volume, that is nothing but at the fixed pressure, that is in the Charles law we are taking at the constant pressure. At constant pressure, volume of the gas, volume of the gas increases, volume of gas increases by increasing the temperature, volume of gas increases on increasing temperature and decreases on cooling. So from this statement, what we understand, volume of the gas increase by increasing the temperature. Otherwise, volume of the gas will be decreases by cooling is nothing but decreasing the temperature only. So from this statement, we can get the conclusion at constant pressure, volume is directly proportional to the temperature. This is the conclusion we can bring from the statement given by the Charles and Gay-Lussac. So V proportional to T. Generally, V by T is equals to constant, like we can write. Then V1 by T1 equals to V2 by T2. If you are taking the two different gases, V by T is equal to constant, V proportional to T, and V1 by T1 equal to V2 by T2. This is one condition. And if you come to the second case, this is the first case, case 1, when we know the statement V proportional to T at constant pressure. Comes to the case 2. What is the case 2 in the Charles law? As we know that a fixed mass of a gas at constant pressure means we are not applying any pressure on that gas. At constant pressure, volume of the gas is directly proportional to the temperature. Then what we find, by each degree rise in temperature, if your temperature is increasing each degree, suppose you have taken at room temperature 27 degrees Celsius, volume is V. You have increased 1 degree Celsius, means at 28 degrees Celsius, V becomes 1 by 273.15 degrees Celsius of temperature. It is increasing to the original volume. That is nothing but the statement we can write here like, for each degree, for each degree rise in temperature, for each degree rise in temperature, volume of gas increases by increasing the temperature. The volume of gas increases by 1 by 273.15 of the original volume. What they observed by number of experiments, the each degree rise in temperature, volume of the gas increases. How much the volume of gas increasing? 1 by 273.15 of the original volume of the gas, it is increasing. Original volume of the gas at 0 degrees Celsius. Excuse me. So, if the original volume is V, then by increasing each 1 degree Celsius temperature, it is increasing 1 by 273.15 times, it is increasing. So, what we can consider here, volume at 0 degrees Celsius is V naught, volume at some temperature, volume at some temperature means 3 degrees Celsius we are considering as Vt. Then according to the case 2, we can write V naught. For every 1 degree Celsius rise in temperature, the volume of the the volume of the original gas will increase, means sorry, Vt is equal to volume at 3 degrees Celsius increases V naught plus V naught plus V naught T by 273.15 times it is increasing. So Vt equals to, if you take common of V naught, 1 plus T by 273.15. So this is called Charles law. This one we can write as Vt into V naught 273.15 plus T by, so 273.15. Here this 273.15, actually it is a new scale we can define here. Generally, T degrees Celsius, T small t means at a temperature at a degree Celsius, here we are considering. The new scale is given by capital T is equal to 273.15 plus small t. It is at 0 degree Celsius. We can write T naught. It is at particular temperature at TT means at particular temperature 273.15 plus T. At 0 degrees Celsius we can write 273.15 only. This is the new temperature we are considering. This new temperature is called Kelvin temperature scale. Means we are converting the degree Celsius into kelvins. That's why while writing in the kelvins, we will not write any degree Celsius again. This is called Kelvin temperature scale. This is called Kelvin temperature scale or absolute absolute temperature scale also we can say. So 0 degree Celsius means it is called the Celsius scale. While talking about the Celsius scale, we will write 0 degree Celsius. This is called Celsius scale representation. Now this 0 degree Celsius scale is equal to the 273.15 K means Kelvin. It will be the converted degree Celsius into the Kelvin scale. While we are converting into the Kelvin scale, again we will not write the degree Celsius here. Okay, so this is Kelvin scale or temperature. Okay, this is also known as thermodynamic scale. So they like this converting whatever the problems we are going to do in the states of matter. Whenever they have given degree Celsius, we'll convert the temperature into the Kelvin's scale by adding 273. Okay, this is a new scale, new temperature scale we'll use throughout this chapter. If they given degree Celsius also, they'll convert into the Kelvins like only. So how can we write now? This 273.15 into T we can write as T capital T, and 273.15 we can write as temperature at 0. Temperature at 0 degrees Celsius is 273.15. Temperature at T degrees Celsius is 273.15 plus T. So, if you modified this relation, then Vt equal to V naught into Tt by T naught. So we can write this is Vt by V naught equal to Tt by T naught. This is nothing but this is volume at some temperature, volume at 0 degree Celsius. Temperature at T degree Celsius and temperature at 0 degree Celsius. So simply this one we can convert, generalize the equation. V2 by V1 is equals to T2 by T1 like we can write. So from this V by V proportional to T, the relation we can bring. This is only no in the case one we have written, that one we have written directly, and by taking the by going to the deep explanation in the case 2 also, Charles and Gay-Lussac they have given this temperature scale and absolute temperature scale also they have been considered. Okay, this is called Charles law. See, this is the mathematical expression for this Charles law states that pressure will remains the constant. The volume of the fixed mass of a gas is directly proportional to its absolute temperature. So now what we can write the Charles law statement, at constant temperature, sorry, at constant pressure, volume of the given mass of the gas is directly proportional to temperature, to its absolute temperature. Okay, see, Charles has considered all for all the gases at given pressure. At given pressure means at constant pressure. Graph of volume versus temperature is a straight line and an extending to zero volume. That is nothing but, see here. Suppose like that, if you are taking volume and temperature, both are directly proportional to each other, then obviously the graph will be just like this, isn't it? The graph, the normal graph of the this one will be like this, will straight line passing through the origin. Suppose if you are extended the temperature, if you have been extended the temperature means, here it is the 0, here it is 100 degrees celsius, it is minus 100, minus 200, it is minus 273.15. So they have taken the graph just like this, at different pressures. See, then the graph at the P1 is this, P2 they have observed like this, at P3, at P4 means at different temperatures they have drawn at different pressures. Why? Because at the given pressure they have drawn the graph between the volume and temperature. And also here, if you are taking from here 0, 100, 200, like that, if you are taking, this is straight line passing through the origin. But the temperature has been extended in this graph. Means we have taken negatives in the temperature, minus 273, 200, minus 100, 0, 100, like that. Then the graph exactly meeting the point minus 273.15. If you observe, already in the previous explanation, that is 0 degrees Celsius is nothing but 273.15 Kelvin, like we have studied. Now we are getting the graph between minus 273.15, 0 degrees Celsius. To convert this one into the Kelvin, we have to add 273.15. Then if this one both will get cancelled and we'll get 0 Kelvin. So if you are extending the temperature, the graph we are getting exactly at the 0 Kelvin. This 0 Kelvin is nothing but called absolute zero. This is called absolute zero. See, this means that gas will not exist. In fact, all the gases liquefied before this temperature is reached. The last hypothetical or imaginary temperature at which gases are supposed to occupy zero volume is called absolute zero. This is not a this is not a ideal, this is actually the ideal gas, like it is does not exist, any gas does not exist this zero temperature. Okay, absolute zero temperatures, the gas will not exist at minus 273.15. Okay, so this is one more case, a special case, like he has considered ma. This is between the volume and temperature. The temperature he has been extended to further. If he extended, then at the different pressures, he has exactly the graph is meeting at minus 273.15 degrees Celsius. That one converted to Kelvin, this is called absolute zero temperature. This absolute zero temperature, no gases are existing, like they have given. So all gases obey Charles law at very low pressures and high temperatures. So the Charles law will be obeyed at low pressures and high temperatures, not at the low temperatures. If low temperature is considering, that gas does not exist. So Charles law, all the gases obeys the Charles law at low pressure and high temperatures only. Okay, this is about the Charles law of case 1 and case 2 we have been discussed, right? Now come to the next one, that is called Gay-Lussac's law. This is easier only. Gay-Lussac's law. Next, Gay-Lussac's law. At constant volume, this one we can consider as the pressure temperature relationship. This one we can consider pressure temperature relationship. So at the given at the constant volume, this is at constant volume, pressure of a fixed amount of gas is directly proportional to the temperature. Then P proportional to T, then P by T equal to constant. Then this one P1 by T1 is equals to P2 by T2 at different temperatures. Sorry, at different temperatures or at different pressures for different gases also we can consider. Here in this Charles law, one important thing. Here we are drawing the graphs at constant pressure. At constant pressure, if you are drawing any graph, that is called isobars. At constant temperature isotherm, at constant pressure isobars, and if you any graph, the graphical representation at constant volume or at given volume, those are said to be isocores. So the graph we are going to draw for the pressure and temperature will be an isocore. Okay, if we take the graph for like this, means it is the pressure and temperature, obviously both are directly proportional to each other at the given volume. Means at different volumes, if you are taking, the graph will be just like this. So v1, v2, v3, v4, obviously v1 is less than v2, less than v3, less than v4. So pressure is directly proportional to the temperature. This is the temperature, it is in kelvins we have taken, it is in bar we have taken. So obviously p proportional to t, straight line passing through the origin, this graph is said to be isocore. The graph is said to be isocore. This is called Gay-Lussac's law, right? So, what is the statement? At a given volume, the pressure of the gas is directly proportional to the temperature. P proportional to T, P by T equal to constant, then P1 by T1 equal to P2 by T2. The graph drawn at constant volume is called the isocore, and the graph will be straight line passing through the origin, right? Now come to the next law. The next law is called Avogadro's law. Next one is the Avogadro law. That is called volume amount relationship. Volume amount relationship. See here in the Avogadro law, volume amount relationship. This is first given by the scientist Avogadro. He has considered with the Dalton's atomic theory and Gay-Lussac's law of combining volumes. We are studying as the Avogadro's law now. It states that equal volumes of all gases, equal volumes of all gases, equal volumes of all gases under the same condition, under the same conditions of temperature and pressure, under the same conditions of temperature and pressure, contain equal number of equal number of molecules. See here, this statement is I'm taking one glass of water. In this glass of water, at constant temperature and pressure, means I am maintaining the same temperature and pressure conditions, room temperature and pressure. It has 10 molecules of water. This one I applied at this place. So I move on to the another place, but I maintain the same temperature and pressure. The same amount of the glass of water will have same number of water molecules. There is no change. If you are taking 50 ml of water, I said 50 ml of water has 10 water molecules. Until and unless changing the temperature and pressure, The same 50 ml of water will have 10 H2O molecules only. If you are changing any temperature and pressure, either the water molecules decreases or increases. That is another scenario. But here you are maintaining the same temperature and pressure conditions, the same volume of the gas under same conditions of temperature and pressure will have equal number of molecules. Suppose I am taking the water vapor or nitrogen gas. I am not changing its temperature and pressure. That nitrogen gas having Avogadro number of molecules. Without changing any temperature and pressure, the same nitrogen gas will have a Avogadro number of molecules. That is nothing but volume is directly proportional to small n, means number of moles. Number of moles. So this one, the we can in place of proportionality constant, I'll take V proportional to K into N, then V by N equal to K. So we can write V1 by N1 equals to V2 by N2. This is a temperature and pressure constant. Volume is directly proportional to the number of moles. Here, then this is V is the volume, N is the number of moles, right? Already we know the relation number of molecules is equal to number of moles into Avogadro number. What is that Avogadro number? Avogadro number represents with Na. It is 6.023 into 10 to the power of 23. This is called Avogadro constant. Okay. This is what this is same. When we are taking the 1 mole, there will be obviously the Avogadro number of molecules will be present here. There is no change in these conditions. So the volume of gas is directly proportional to the number of moles. Then 1 mole of each gas, 1 mole of each gas, because volume is directly proportional to n number of moles, then 1 mole of each gas at STP or NTP. STP is nothing but standard temperature and pressure conditions. NTP is also normal temperature and pressure conditions. At STP, 1 mole of each gas will have same volume. At standard temperature and pressure, means temperature will maintain 273.15 Kelvin temperature at STP, and the pressure will be 1 bar. Pressure will be 1 bar and exactly 10 to the power of 5 pascals also we can say. 1 atmosphere is equal to 1 bar. Already we also know that relation. At STP, temperature will be 273.15 Kelvin. Pressure will be 1 bar. These values are approximately at freezing temperature of water, and atmospheric pressure at sea level, means we have taken these as the fixed. At STP, molar volume of an ideal gas, temperature, pressure and volume also will be generally 22.4 like we'll consider, but it has been changed nowadays. It is writing as 22.7 liters per mole. These are called molar volume. So at STP, temperature should be this much, pressure should be this much, and volume should be considered as this much. 22.4 actually, that has been modified as 22.7 liters per mole. Got it? So these are the standard temperature and pressure conditions, while 1 mole of each gas at STP conditions. Right? So here we can bring some more relation, that is number of moles formula we have. Number of moles small n equal to given weight by gram molecular weight. Small m is nothing but given weight. Capital M is nothing but molecular weight. Small m by capital M. So V is equal to K into small m by capital M. Right? So capital M is equal to K into M by V. This is called mass by volume, is called density. So molecular weight is equals to K into density. This is also one more relationship we can bring. Right? So here D is the density of the gas, and we can conclude from this equation, that is the density of a gas is directly proportional to its molecular weight or molar mass. Capital M is the molar mass also. Density is directly proportional to the molar mass, like also we can conclude. So today we have discussed the four important gas laws. First one is the Boyle's law, Charles law, Gay-Lussac's law, and Avogadro's law. Right? Now come to the very important one is called ideal gas equation. Ideal gas equation. So what is ideal gas equation? Ideal gas equation nothing but ideal gas. What is meant by ideal gas? According to the Boyle's, Charles, and Avogadro's law, strictly called an ideal gas means a gas which follows all the three gas laws. A gas which follows all the three gas laws is called an ideal gas. But such gas is not existing. That is an hypothetical condition because the intermolecular forces are not present between the molecules of an ideal gas. Real gases can follow. Real gas means these helium, nitrogen, hydrogen, oxygen, whatever the gases we are taking, those. But those real gases cannot obey to all the ideal gases at the given conditions. Under specific conditions, when the forces of attractions are negligible, then the real gases will behave like as an ideal gas. Until and then there is no ideal gas is existing. So what is this ideal gas equation? The gas which obeys all the three gas laws. What is the three gas laws means Boyle's law, Charles law, Avogadro's law. Boyle's law. What is Boyle's law? At constant temperature, pressure is inversely proportional to volume. This is Boyle's law. What is Charles' law? V proportional to T at constant pressure. It is at constant temperature. This is called Charles' law. What is Avogadro's law? Volume is directly proportional to N. Right? This is also at constant pressure and temperature. V proportional to N. This is called Avogadro's law. So the gas which obeys all these three gas laws, that is said to be the ideal gas. So this one is 1, this is 2, this is 3. From 2 and 3, V proportional to T into N, like we can write. Isn't it? From the first, P proportional to 1 by V. So this one we can write as V proportional to 1 by P. So again, V proportional to 1 by P, so it can be modified P into T into N by P. Because volume is directly proportional to temperature, directly proportional to number of moles, but inversely proportional to pressure. That is what we written here. If you remove the proportionality constant and I am keeping R, then N into T by P. This R is nothing but called universal gas constant. This R is called universal gas constant. So we can write V equal to R into N into T by P. Then PV equals to R into N into T. This is called ideal gas equation. P is called pressure, V is called volume, R is called universal gas constant, N is number of moles, T is the temperature. T is the temperature. So this is called ideal gas equation. So here we have a different R values and we have a combined gas law like that. Those we'll study in the next class, which is the next class. In the next video, we'll discuss Dalton's law of partial pressure. Okay, Graham's law of diffusion, like. Okay, guys, thank you. Thank you so much. Please do subscribe to my channel. If you have any topics, that topic you can comment in the comments box. Then I'll choose the topic and I'll do the video on that particular topic, guys. Okay. Thank you. Thank you so much.